Right, I think that's finally working. Okay, so normal subgroups and factor groups. So we've just been doing the chapter on isomorphisms, but this is where we kind of start with here is we're going back to when we did Lagrange's theorem, cosets. Okay, so what we looked at with cosets was cosets gave us a way that when we started with a subgroup, so we start with any group G, we start with a subgroup H of it. And when you looked at the cosets of H and G, what you're actually looking at was a partition of the group G into partitioning it into a set of subsets, one of which was the subgroup H, and the other ones are these kind of translations of H, if you like. And what we're looking at in this chapter is the special situation where that partition of G, that set of subsets of G, can actually be given a group structure itself, can actually be turned into a group, it can actually be seen as a group. Now, it only happens in special circumstances. The circumstances where it happens is where the subgroup is what we call a normal group. And we'll look at a normal subgroup of the group G. And we'll look at that definition closely now soon. But in short, the definition is that if you have your subgroup H and you take any element little g from the group G, if it's always the case that the left coset corresponding to G is the same as the right coset, then the subgroup is termed a normal group. Okay, so the partition provided by the left cosets and the other partition provided by the right cosets, when the group is normal, those two partitions are exactly the same. There's the same splitting of G into the same set of subsets. And in this situation, it's possible to give a very natural group structure to the partition, meaning to the set of subsets. You're not dealing with individual elements from the group G now, you're dealing with subsets of elements. So you group together subsets of elements of the group G, you're regarding all of the ones in the same cell with the partitions being equivalent, you're treating them as one single object. And there's a very natural way to multiply together these subsets that's induced by the multiplication, by the operation you already have in the group G. One way in kind of embodying in a nutshell what this is, the new group is called a factor group. Factor group of the group G by H. It's also commonly called, I think more commonly called a quotient group. I think that term is more common in the literature, but factor group is what we're using in this book. It's a kind of a simplification of the original group G. It's taking the original group G and producing a new group out of it, which is a simplified one. It's going to be a smaller group because the elements are subsets of the original set G. So they can't be more, they can't, when you split the group G and partition it into subsets, there can't be more subsets in that partition than there are elements in the original group because you're lumping elements together. You're going to have a smaller number of elements in this new group. And the new group carries through some of the features of the original group. And in a way, what the factor group is doing is it's looking at the original group G and it's showing you what happens when you regard all the elements of H to be equivalent to the identity element. You regard all the elements of H as being somehow null or equivalent to the identity element. And then looking at the ramifications of that. What are the consequences of that? Okay, so that's kind of like an overview of the whole thing. So we're going to work through it now in careful detail and look at some examples. So what you find in chapter 10 is introducing the key definitions along with several examples and proving this key result that the set of subsets in the partition that provided by the cosets of H and G, that actually is a group. And the second section, 10.2, looks at this important result about the alternating groups. So in a sense, when a group G, when it does have a normal subgroup, when it's possible to reduce the original group G by looking at a factor group of it, that in a sense is saying that the group G has a kind of rich or complicated structure, that it's possible to reduce it down in some ways. So of special interest are the groups that are already as reduced as possible. So special interest are groups that you can't reduce them down any further. In a sense, almost like prime numbers, maybe in a way. Prime numbers you can factor into simpler, into products of simpler numbers. So in a kind of similar way, groups which do not have any normal subgroups are of special interest because they're already in some senses as simple as possible. And indeed, simple is the technical term that's used. A simple group is one which has no proper normal subgroups in it. And the alternating groups, AN, whenever n is greater than or equal to 5, remember the alternating group is the set of all even permutations of n objects. And these are important examples of simple groups. Okay. So that's just a quick introduction. There's also reading notes there on chapter 11, but we'll tackle chapter 11 next week, I think. So let's have a go. Let's have a talk through what we've got there in chapter 10. Any questions before we start? Okay, so we'll just consider the important definitions. We'll have a look at some of the examples, and we'll fill in some of the detail in some of the proofs that we have. Okay. So the first thing we want to look at is the definition. Okay, so normal subgroups and factor groups. Okay, so we're talking completely general. So a subgroup H of G. G is some large group. H is a subgroup of it. It's called normal. Normals, or let's say normal in G. A normal subgroup of G. Now what's the definition of this? If and only if. Well, let's just get the short and sweet, kind of compact, logical definition of it. If and only if for every group element little g times h, with little g on the left, is always the same as little g times h, but with little g on the right, okay? So, i.e., in words, what we're saying there, every left coset is equal to the corresponding, by corresponding, I mean, i.e. the same element G. So no, little g. Every left coset is equal to the corresponding right coset. So for every element little g from the group, the left coset corresponding to the element little g is equal to the right coset, okay? So you no longer have this ambiguity whereby you can partition G in one way using left cosets, and maybe the partition by right cosets is different. When the group is normal, so we can speak of the partition of G by cosets of H, i.e. no need to specify whether we're talking about left cosets or right cosets, because they both are exactly the same. Okay. So that's the definition. Let's look at a couple of examples. So the first example in example 10.1, well, this is kind of like a little result in itself. So example 10.1, in any abelian group, Remember, an abelian group is one where the group operation is commutative. Okay. Well, you know, this is a commutative type condition, the condition of normality. So if everything is commutative anyway, it's not surprising that every subgroup is a normal subgroup. Okay? So in any abelian group, every subgroup is normal. Okay, because in this case, a left coset, that's equal to the set of all GH, where H is in H, but that's automatically equal to the set of every little h times G. Why is that true? Because G times H is always exactly equal to the element little h times G. And then this set is simply the definition of the right coset of H corresponding to the element little g. Note that the normality condition isn't saying this. Okay. This condition up here does not say that little g times the element little h is equal to little h times little g. It's saying that if you look at the set of all the elements g times little h, that will be the same set as all of the elements little h times g. But if you focus on a specific little h, it's not necessarily the case that g times that little h is equal to the same little h times g. It'll probably be the case that g times a specific little h is equal to one of the other little h's in the subgroup h times g. Okay, so it's on a set level, these two are equal. That's the definition of normality. But in abelian cases, something much stronger holds. Everything commutes with everything else. Every element commutes with every other element. So in particular, every g times little h is equal to exactly the same h times the same little g. So the left coset is always the same as the right coset. Okay. So of more interest is looking at non-abelian groups where we have normal subgroups. So the suggestion is that in non-abelian groups, some subgroups are normal and some aren't. That's what we expect. Okay? And indeed, that's the case. So, I think we've seen these examples already when we looked at the cosets chapter. So recall S3 and its subgroup. So the first example is a negative one. So this first subgroup is the one consisting of the identity element and a single transposition. Okay, so the permutation permuting the elements 1 and 2. This subgroup is not normal, and you can see that when you look at what you get when if you look at the coset corresponding to the 3-cycle 1, 2, 3. Okay, that certainly contains 1, 2, 3. So when you multiply 1, 2, 3 by the identity, you just get 1, 2, 3. But when you multiply 1, 2, 3, and on the right of it put the transposition 1, 2, you get 3-cycle 1 goes to 3. 1 goes to 3, don't you? Yeah, just the transposition 1, 3. Okay. 1 goes to 3, 3 goes to 1, and 2 will go to 2. Okay, because when you put the transposition 1, 2 on the right of 1, 2, 3, 1 goes to 2, and then sorry, I'm interested in looking at the image of 2. You put this transposition 1, 2 on the right here, 2 goes to 1, and then 1 goes back to 2. So 2 goes to 2. Just like this. Okay, but when you look at the right coset here, H and 1, 2, 3 on the right, you again get this, the right coset, again, it has the 3-cycle 1, 2, 3, but the other element in it is different. Okay, so what do you get here? So when you put 1, 2 on the left here, 1 gets sent to 2 by the 3-cycle, but then 2 gets sent back to 1. So this one doesn't operate on 1. 1 is the identity, where 1 is left unchanged. So you just get the cycle 2, 3. Okay. So these two sets are different. Okay. So the corresponding to this element, at least, the left coset is not the same as the right coset. Okay. And it will probably hold true, perhaps, for the other 3 cycle as well. Not sure about the other transpositions. Okay. But at least in this case, it breaks down. Okay. So this H is not normal. So this H is not normal in S3. But that's not to say that S3 doesn't have any normal subgroups. It does. Indeed, the next example. Whereas if you consider H, or let's say N, whereas N, this subgroup consisting of, well, this is a cyclic subgroup generated by the 3 cycle. Okay. So the subgroup consisting of the identity element and the 2 3 cycles in S3, that's a subgroup of S3. This is now a normal subgroup. Okay. This is a normal subgroup. Okay. And the only, you see, how many things does S3 have in it? S3 has 6 things in it. Remember, the order of Sn is n factorial. So the order of S3 is 6. The order of this subgroup is 3. So there's only going to be 2 cosets. Remember, every coset has the same number of elements as every other one. So the 3 elements in the normal subgroup itself. In the other coset of it, there's going to be another 3 elements. That's going to be all the elements of S3. And remember, different cosets are distinct. So this coset here, when it's the left coset corresponding to the transposition 1, 2. But when you multiply 1, 2 by the identity, you get 1, 2. So already we see it's a different coset because it's not exactly the same as this one. So it has to be completely disjoint. So this has to contain the other 2 elements from S3, which are the other 2 transpositions. Okay, that's the other left coset. But if you look at the right coset, there, I mean, that has to be the same set of elements as well. Because the right coset corresponding to the transposition 1, 2, it again has to contain the transposition 1, 2. And you must put the identity element from n on the left of 1, 2, you get 1, 2. And this is a different coset to the original coset n, so it has to again contain the other 2 elements as well. Okay, so you see the left coset is always the same as the right coset. So this n is normal. So this n is normal in S2. Okay, any questions about those examples? Okay. So there are lots more examples to explore. We'll encounter some more of them as we go through the chapter. Okay. So it can often be, if you're investigating a particular group, it's often a relevant question to ask about any particular subgroup of it. Is this subgroup normal? If you know the group is abelian, then you know the answer is automatically yes. Okay, every subgroup is normal. If the group is non-abelian, as S3 is, and most interesting groups are non-abelian, then some of the subgroups might be normal, some of them might not be. Okay. Now the first results, which we have here, is theorem 10.3, is, we quite often see this, when we introduce a new concept and give a definition, there's often alternative ways to think of the definition, equivalent ways to think of the definition. Okay. So this gives three equivalent conditions for normalcy. Okay. So these could be taken as 3 different ways of defining what a normal subgroup is. So the first of them is just the original subgroup, the original definition. So N is normal in G, as defined above, meaning for every element G, the left coset corresponding to little g is the same as the right coset. Okay. The second condition, now they're very closely related types of things. Instead of phrasing it as we have done, instead we can phrase it like this. When you take any element little g, and remember we referred to this concept as conjugation. When you conjugate the subgroup by a little g, so you pre-multiply it on the left by g, you post-multiply it on the right by g inverse. So this by definition is the set of all elements that perform g times a little n times a g inverse. Okay, all of those elements. But this is actually, what's it saying? This is actually contained in the same subgroup n. And the third condition is just that, you know, it's maybe not something different. It's just a slight restating of that. Is that g and g inverse is actually equal to n. So I mean, really, are these three separate? Definitely. I mean, really, I think the one to concentrate on is this one here. You know, it's easy to see that 3 certainly implies 2. You know, if these two sets are equal, certainly this one is contained in that one. Okay. But it just gives us, you know, from time to time, rather than dealing with the original definition, we'll prefer to deal with this kind of condition here in 3. Okay. So if you like, we could have alternatively, this is the definition of a normal subgroup. I won't talk through the proof of this. You can read through the proof of it there. It's at the top of page 170. It's just straightforward, just argument from the definition. There's nothing surprising in it. But what I will say is make some comments here. So this kind of construction, G and G inverse, is called, as I said, the conjugation of n by g. Conjugation is this operation of post-multiplying by a certain element, pre-multiplying by a certain element, multiplying on the left by a certain element, and multiplying on the right by the inverse of that same element. Okay. But this is an interesting operation. For any subgroup H of G, so I'm just talking about any group here at all, we can take an element little g in the group G and form the subset well, which is the conjugation of H by G. So you take any subgroup at all, you can form the subset GHG inverse. So this by definition is just the set of all these elements GH, G inverse, whenever H is an element of the subgroup H. Now, what do you think I'm going to say about this? I'm going to say something about this subset. What do you feel like I'm going to say about it? And if H is a subgroup, when we conjugate it by an element, we get another subset of G. This is certainly a subset of G. To say something more about it would be to say that this is again a subgroup of G. Okay. So we can form this subset, and this subset is again a subgroup. Of G. Is there much to do to prove that? Yeah, we could throw down a quick proof of that, or I could leave it as an exercise. Well, let's just throw down a sketch of that. What do you have to prove for a subset to be a subgroup? Well, we could look back. We had a subgroup theorem. But essentially what we need to do is prove that it's already a group. Prove that it's a group under the same operation as G. So that boils down to being sure that it's non-empty. Well, it's clearly non-empty. It's a set of products. And H is a subgroup, H is non-empty, so there are these little H's. So it's clearly non-empty. It must contain the identity. It must be closed under the operation, and it must contain the identity in inverses. So GHG inverse clearly non-empty, since H is. I guess we should deal with closure first. Closure. So what do we mean by closure? It means if we take two elements there's two elements, one in the left bracket, one in the right bracket. These are two elements from GHG inverse, yeah? So it's G times some little H, G inverse, and G times maybe another little H, G inverse, okay? What do you get when you multiply those together? Well, by associativity, you just ignore the brackets. You just have to multiply them together in this order. But you see G inverse and G are beside each other. So they cancel out. So what that is equal to is G H1, H2, G inverse. And this will be an element of G, H, G inverse whenever H1 and H2 are elements of H, okay? Because this product here, H1, H2, that would be an element of H. So again, you're looking at something of the form G times an element of H times G inverse. So this is certainly an element of this. Yeah. So it's closed under the operation. You take two things from this set, multiply them together, you're again in the same set. So that's a good candidate for a group. You look at the identity. Can we say that the identity is present? Okay, because remember, a subgroup has to contain the identity. Well, can we write the identity as G times something times G inverse, where the something is from the subgroup H? So I got to fill this gap here with something from H, and I want it to be equal to the identity. I want it to be in. So what's the element from H that I take to get the identity here? What's the one element of the subgroup H that you're able to name? Yeah. The identity. Yeah, I mean, we're talking completely generally here. H is just some subgroup of some group G. I haven't given you any context, any information about it. So the only element of H we're able to point to is the identity element of the group G. And yeah, if you have the identity element there, it doesn't change. You know, you can multiply it by this G and it'll leave the G unchanged, and then you'll be multiplying G by G inverse, which is the identity. Yeah. So yeah, we can form the identity as G inverse, and that will be in GH G inverse, since E is an element of H. So the conjugation of H by G, it contains the identity element. It's closed under the operation. So I think now the only thing we have to prove now is that it contains inverses. Okay. So if you let GH G inverse be an element of GH G inverse, then we want to examine the inverse of this. I want to we want to be sure that the inverse of this element is again present in GHG inverse. Now, how do I do? So at the moment, I don't know. I take an element, G times a little h times a G inverse from the conjugation of H. What do I know about the inverse of it? Is there any way that I can develop that expression? So how do you take the inverse of a product? How do you take, there was a nice saying or mnemonic that we had, or a nice slogan that we had for this. The inverse of a product of elements. If you like, you can think of something more concrete like matrices. Imagine these are matrices multiplied together, as they might be if we were in the context of matrix groups. So how do you take the inverse of a product of a bunch of matrices? Well, it's going to be the product of the individual inverses. There's an extra crucial bit you got to add on there. You have to reverse the order. The inverse of a product is the product of the inverses, but in the opposite order. So the inverse of this triple product here, I take the inverse of the last element, multiplied by the inverse of the middle element, and then multiplied by the inverse of the first element. Okay? This is basic property about inverses of products. The inverse of a product is the product of the individual inverses, but in the opposite order. And of course, how do I simplify this further? What is the inverse of G inverse? It's just simply G. Yeah. So G times H inverse times G inverse. And where can I say this element is? Is this element again in this subset? Well, yeah, it's G times something from H times G inverse. And this something from H inverse, that is in capital H because capital H is a subgroup. The little h started off as something from capital H, so its inverse is again in the capital H. So this is certainly an element of the conjugation of H by G. So that completes the proof that the conjugation of a subgroup by an element of the containing group is again a subgroup of the containing group. So GHG inverse is again a subgroup of G. Again, meaning just if H is a subgroup, then GHG inverse is a subgroup. How many elements do you think are in GHG inverse? GHG inverse consists of all products we can form, like G times a little h times G inverse for any h and little h, okay? So it actually consists of the same number of elements that are in H, okay? So it's a subgroup even of the same type or level, yeah? It's again a subgroup of G, and it contains the same number of elements that H has, okay? Strictly speaking, you have to prove that. You have to consider what would happen if G times H times G inverse was equal to some other G times a H times a G inverse. But by cancellation law, you would tell that the two H's had to be the same. So GHG inverse is again a subgroup of G, and it's of the same size, or the same order. I'll use the word size, descriptive. It's of the same size as H. So conjugation is a way, if you like, of generating subgroups. If you start off with a subgroup, conjugate it by something, and you might get a new subgroup, okay? So this gives us another way to think about this concept of normal subgroups. So in general, when we take any old subgroup of a group G, conjugated by an element, we have to be prepared to expect that this will be a new subgroup of G, a different subgroup of G to the one we had, okay? In general, that will be true. So it's a special case when it happens to be exactly the same subgroup, okay? So we can we can, if we want, take this as our alternative definition of what a normal subgroup is. It's a group such that when you conjugate it by any element, you get the same subgroup back again. In general, you would get a different subgroup, but in this special case, you always, for any element like G, you are always going to get the same subgroup back. That's the definition of being a normal subgroup. Is that okay? That's just a bit of background, a bit of context. So this operation of conjugation comes up all the time in group theory. It's a very natural way of moving around a group, building associated things by conjugating. Okay, so that brings us then to the definition of this new group. Okay, so to the definition of the concept of factor groups. So, and a rough Venn diagram is, we've got our original group G, we've got a normal subgroup of it. Okay, so this is a special kind of subgroup. It's at least got the identity element in there, and it'll probably have a bunch of other elements of G in there. Okay, and there's a partition that we can build of G by the cosets of n in G. And I don't have to say if I'm talking about left cosets or right cosets, because they're the same thing. Okay, so it's just unambiguous that I'm talking about cosets of n. Okay, so this will be a G1n up here, which is equal to ng1 on the right. Okay, so this is just one of the cosets here. I'll have a G2n, etc. Okay, so a bunch of different cosets. Okay, so we have the partition of G by a normal subgroup n consisting of how many cosets? How many cosets are we looking at there? How many cosets are there? Well, okay, 1, 2, 3, 4, 5, 6, 7. Okay, the answer is 7. This is 7 in that particular drawing. But in terms of the information there, how many cosets are we looking at? Well, remember, if G is a finite group anyway, if G is a finite group to begin with, because most of the interesting groups that we're looking at here are. If G is finite, n will be finite. Okay, and remember the argument in Lagrange's theorem, all the cosets have the same number of elements. So they all have the same number of elements as are in n. And that has to be a divisor of the group G. So the number of cosets we're looking at is the size of G divided by the size of n. In the case where G is a finite group. So the general term for this number is, remember, we have this in chapter 6, the cosets chapter. We call this the index of n in G. The index of n in G, where for the special case where G was a finite group itself, this is simply just a fraction. The number of elements in G divided by the number of elements in n. For different cosets. In the case where G is an infinite group, then we don't have that form to speak about because there isn't, you can't form a fraction with infinity at the top. So we just have this concept that the index of n and G is the number of cosets that we have. Okay, so for this new group called the factor group, the set of elements that we have is the set of cosets. Okay. So we need an operation on them. Okay. So the set of cosets. So that means I'm no longer focusing on the small dots as elements. Now this is one element. This is another element. Okay. So it's the cosets themselves, the subsets of G themselves, which are the elements. So the set of cosets of n in G forms a group under the operation. So here's the thing, what's the operation? Well, if I want to define the operation, I have to tell you how to take two cosets of n and g and how to multiply them together. How to multiply these two together to give you what kind of object? Well, I'm trying to form a group on the set of cosets, so it again has to be a coset of n. And okay, I know left cosets, they're the same as right cosets, but I'm just always going to write things as left cosets. We'll take that as our standard way of presenting things. So which left coset could it be? Now, what I'm trying to get across to you here is how natural this operation is. How there's really only one obvious candidate choice for which left coset I'm talking about. I mean, the inputs into this operation are the left coset corresponding to G1 and the left coset corresponding to G2. So of all the things I might put down here, there's one that kind of stands out as the most obvious thing to put down, and that is simply the element G1 times G2. It's the most natural way to combine these two. So when you're looking at this here, what you should see this as this single group element, G1 times G2, and we're talking about the coset corresponding to it. Now, what do we have to think about here? Okay, so that's the claim. That's the claim. Okay, the claim is the set of cosets forms a group under this operation. So, okay, well, we'd have to prove that. Okay, so we'd have to prove it's a group. So that would mean we'd have to prove that it's closed under this operation. Well, it's kind of closed by definition because this output, the answer it gives, is always a left coset. We'd have to show it contains an identity element. That's going to be the coset E times n itself. We're going to have to show that the operation is associative, and we're going to have to show that every element has an inverse. So for every coset in here, there's another coset, or maybe the same coset itself, which is the identity element. So that's clear that we're going to have to do that to prove that this is a group. But there's something we have to prove even before we start doing all that. Before we start doing all that, we have to prove that this operation is well defined. We need to be sure that this operation is well defined. This is most of the work in theorem 10.4. Now, what do I mean when I say well defined? I mean, it looks well defined. Here's a left coset, here's another left coset, here's the resulting left coset. But the problem is that I've declared the value of the product with reference to these two elements, G1 and G2, from these two up here. Okay. But now, so G1 is just one of the elements. G1 is one of the elements in this coset here. G2 is one of the elements in this coset here. You have to think about the possibility, well, what if I didn't choose G1 over here? What if I chose a different element but from the same coset? And what if I chose a different element over here to G2, but still in the same coset as G2? So in other words, what if I chose different representatives of these two cosets? Not necessarily G1, not necessarily G2, but still representatives of the same cosets. Then you see I'd have a different group element here. So I'd be multiplying together two different elements. So what we need to show is that if you do choose different representatives here, you multiply them together, you get a different representative, you get a different element here. But it will still be an element of this same coset. Okay. So when you take G1n and G2n, by definition, this gives you this coset over here, let's say, which is G1, G2, that element, times n. So that's G1, G2 times n. But to prove it's well defined, we have to prove that, well, if you take a different element from here and a different element from here, the rule, when you try to evaluate this using a rule, you're going to get a different group element over here. But it will just be one of the other elements in here. That's always the case. Okay. So there is this task left that this definition is not enough on its own. Okay, it looks like a candidate for a good, well-defined operation, but it does need to be proved better. Okay. So we have to be sure that this operation is well-defined, and this is most of the work. Most of the work done in theorem 10.4. So I don't want to rush through it now. So we'll discuss this we'll discuss this point on Friday and look at some more examples and exercises. Okay. What is it? So once we're sure that this is indeed a well-defined operation, I mean, it looks reasonable, seems reasonable. When we're sure it's a well-defined operation, so that we can actually confidently speak of it as an operation on the cosets themselves, then we can quickly check the group axioms that it is closed, it is associative, there is an identity, and there are inverses. And then we'll know that indeed we have successfully formed a group in this new this related system to G. So you can kind of get the impression just from this diagram how it is indeed a kind of simplification of the group G. G on the original detailed level is all these individual points, all these individual group elements, and the way that they multiply together. But the factor group of it is taking a certain special type of subgroup of it and saying, well, all these elements here I'm going to regard as just a single object. And then you get kind of shifted copies of n, these other cells in the partition. Now I'm going to get a new group now, which is just these much less number of objects, but just consists of these new objects, and there's a group structure on them. But it comes from the group structure on G. So the definition of the operation between two cosets relies upon the definition of the operation in G. But it's kind of like looking at G through kind of smoky glasses or bad glasses. So you can't see the individual elements of G. All you can see is this larger scale structure. All you're seeing is just the different cells in the partition. It's like on the one hand, looking at Britain, say, it's seeing all the individual people, all 70-odd million of them hovering around in Britain. But then maybe, okay, well, that's the original Britain, that's on the full level of detail, but maybe you get a simplified view of it, and you look at it, and all you can see are the three countries of the mainland Great Britain: Scotland, England, Wales. So it's a much simpler view. All the people in England, you're clumped together. All the people in Scotland, you're clumped together. All the people in Wales, you're clumped together. Or maybe a more intermediate level is, say, to look at it on the level of the counties. I don't know if the counties are, not just, Hampshire, Devon, Cornwall, So you're splitting the full detailed picture of individual people, clumping all the people together on some kind of meaningful way into cells. That's something like what's going on here. Okay, so we'll discuss this further on Friday, and we'll have a good look at that important theorem 10.4 and some of the examples and exercises. Okay. But in the meantime, in advance of that,